Hello everyone, I'm Lian Zheng from the Institution of Automation, Chinese Academy of Science. Today is a very great pleasure indeed for me to be able to attend this meeting. Today, I would like to present my paper, ARVC, an autoregressive voice conversion model without parallel training data. My presentation contains of 4 parts, including motivation, proposed method, experiments, and conclusions. Firstly, I will introduce the motivation of this paper. Voice conversion aims to modify the source speaker's voice to sound like that of the target speaker while keeping the linguistic content unchanged. The conventional voice conversion approach usually needs parallel training data, which contains pairs of the same transcription utterance spoken by different speakers. Parallel voice conversion first aligns acoustic units between source and target speech by DTW. Then, a conversion model is learned to map speech from source to target speaker. Several statistical conversion models have been proposed, including GMM and neural networks. Recently, the sequence-to-sequence model with attention has been studied for parallel voice conversion. Compared with conventional methods, this method can achieve better naturalness and speaker similarity. However, problems such as mispronunciations and training instability have also been observed while training the sequence-to-sequence voice conversion model. When parallel training data is unavailable, there are also some methods for non-parallel voice conversion. VAE has been successfully proposed for non-parallel voice conversion. However, VAE suffers from over-smoothing. To address this problem, GAN and its variants use a discriminator that amplifies this artifact in the loss function. However, these methods are hard to train, and the discriminator's discernment may not correspond well to human auditory perception, thus degrading the sound quality of the converted speech. Recently, there is another track of research that applies PPGS for non-parallel VC. PPGS are the frame-level linguistic information representations obtained from the speaker-independent ASR system. The PPGS-based voice conversion framework mainly have two key components, the conversion model and the vocoder. The conversion model converts PPGS extracted from the source speech into acoustic features of the target speaker. Then the vocoder uses this converted speech to synthesize the speech waveform of target speaker. However, in practice, we find that the trajectory of some converted waveforms is not smooth, thus causing some voice errors. In this paper, we propose a new autoregressive model for any-to-one voice conversion, called ARVC. As shown in this figure, ARVC produces the next step acoustic features based on two inputs, the predicted acoustic features of the previous step, the PPGS extracted from the source speech. Our ARVC is an extension of conventional sequence-based voice conversion system and the PPGS-based voice conversion system. Compared with conventional sequence-based voice conversion system, ARVC removes attention-based duration models, since PPGS already contains the duration information, thus reducing mispronunciation and improving training stability. Compared with conventional PPGS-based voice conversion system, ARVC takes previous step acoustic features as the inputs to produce the next step outputs via the autoregressive structure, thus generating smooth trajectory and causing less voice error problems. We conduct experiments on the CMU Arctic American English database. It contains 4 native American English speakers, and each speaker has multiple sentences. Our voice conversion experiments are conducted on these 4 speakers. Intergender and intergender conversions are conducted between following pairs. For comparison, we implement the following state-of-the-art baseline methods to comprehensively evaluate the performance of our proposed method. System 1 employs speaker-independent ASR and KLD-based mapping approach to voice conversion without using the parallel training data. The acoustic difference between source and target speakers is equalized with speaker-independent ASR system. KLD is chosen as a distortion measure to find an appropriate mapping from each input source speaker's frame to that of the target speaker. Finally, the straight vocoder is used to generate the converted waveform. In System 2, it achieves top rank on naturalness and speaker similarity in Voice Conversion Challenge 2018. Firstly, the acoustic features of the source speaker are converted towards the target speaker using an STM-based conversion model. Then, the waveform samples of the converted speech are synthesized by sending the converted acoustic features into the WaveNet vocoder built for the target speaker. We conduct objective evaluations to assess the effectiveness of our proposed method. MCD is employed as the objective measure to evaluate how close to convert the speech is to the target speaker. Ideally, the lower MCD indicates the best performance of the voice conversion model. Experimental results show that our proposed method outperforms System 1 in all conversion pairs. The reason lies in that System 1 uses the straight vocoder for speech generation, while System 2 adopts the ARVC vocoder to reconstruct the waveform from the converted acoustic features. These results verify the advantages of the ARVC vocoder for speech generation. Meanwhile, our proposed method outperforms two baseline methods in all cases. By fitting previous step acoustic features to predict the next step output via the autoregressive structure, our method generates more smooth trajectory of waveforms. Therefore, our ARVC achieves better performance than System 1 and System 2. Following previous works, the quality of the speech samples and their similarity to target speaker are evaluated using the subjective evaluation. The Morse tests are conducted to assess speech quality. Meanwhile, we conduct the same different paradiagram to assess speaker similarity. The results of subjective evaluations are presented in these figures. This figure shows the MOS test results, and this figure shows the similarity test results. Results suggest that the performance of our proposed method significantly outperforms that of the System 1 in all the conversion pairs. These results suggest that the ARVC vocoder significantly outperforms that of the straight vocoder in terms of speech quality and speaker similarity. As shown in these figures, experimental results also show that our proposed method achieves slightly better performance than System 2 in all cases. Meanwhile, from the additional listeners' feedback, we observe that our proposed method suffers from less voicing error problems compared with System 2. Compared with System 2, our proposed method takes previous step acoustic features as the inputs to produce the next step output via the autoregressive model. Therefore, our ARVC can generate a more smooth trajectory and achieve better performance than System 2. In this paper, a novel ARVC model is proposed for voice conversion called autoregressive voice conversion. Compared with conventional PPGS-based voice conversion, ARVC takes previous step acoustic features as the inputs to produce the next step output via the autoregressive structure. Then, the ARVC vocoder uses these predicted acoustic features to synthesize the speech waveforms of the target speaker. To verify the effectiveness of our proposed method, we conduct experiments on the popular benchmark database CMU Arctic. Experimental results show that our proposed method outperforms two state-of-the-art baseline methods in terms of speech quality and speaker similarity. Meanwhile, from the additional listeners' feedback, we observe that our proposed method suffers from less voicing error problems. Finally, thanks for your attention.